Welcome friends. In this new video we will discuss about a famous theorem about an integrability of a function given by a Darboux. F is a bounded function on closed interval a comma b, then to every epsilon greater than 0 there corresponds delta greater than 0 such that number 1 upper sum for p, upper sum of a function f for a partition p is less than upper integral of f plus epsilon, and lower sum is greater than lower integral of f minus epsilon. This is to for every partition p of closed interval a comma b with the norm of p is less than delta. Now let us prove this. The very first line of this theorem shows that the function is bounded. The function must be bounded. So we assume that the function is bounded and upper bound of this function is k. So first let f be bounded on closed interval a comma b, then there exists k greater than 0 such that mod of f of x is less than equal to k. The function is given as a bounded function. Now come to the definition of upper sum. What is the definition of upper sum? Upper sum is upper supremum into length of that summation of supremum into, this is upper sum, UPF equal to summation of capital Mi into delta xi, and upper integral is infimum of this upper sum. This is an infimum value. That means when we add something to this value, there must be one member of this set less than this one. This is an infimum value. No value smaller than this or greater than this is infimum. Therefore, we can write this as there exists a partition P1 having points x0, x1 dash dash xp such that this UP1f is less than upper integral plus 1 by 2 epsilon. Okay, look at this. If we take the interval, suppose my interval is 1 by 1 to 2, this is 1 and this is 2, then you can see that this is an open interval. What is the infimum? Infimum of this is 1. Infimum of open interval 1 comma 2 equal to 1. So that if we take 1.1, then there exists, suppose this is my number, this is an point x, then there exists one point, for example 001, which is greater than 1 and smaller than 1.1. so there this number is smaller than 1.1. okay, and this is a member of this set. So similar criteria is applied here. If this upper integral is an infimum of this upper sum, then there must exist at least one partition P1 such that x0, x1, x2 and xp, where xp1 up1 f is less than upper integral plus 1 by 2 epsilon. Let us call this as a equation number 1. Now here this P1 contain how many points? This P1 contain P minus 1. P1 contain P minus 1 points besides x0 is a and xp equal to b. So if we take another partition, suppose if we have p2 equal to another partition y0, y1, y2 dash dash yq, then y0 is equal to a and yq equal to b. So these are the common points to these partitions, right? So if we leave these points x0 equal to a and xp equal to b, we have p minus 1 points in partition p1. Now let us take p star be the refinement of a partition p and p1. So we are taking two partition p and p1. Okay, so these are the two partition in our assumptions. We have p1 having p plus 1 points and p minus 1 are the points different from this, besides this x0 equal to a common points x0 equal to a and xp equal to b. Let us make some assumptions. Now here we take this p1 points are in a such way that we choose delta such that this 2k p minus 1 equal to here 1 by 2 epsilon, 2k p minus 1 into delta equal to 1 by 2 epsilon, and this partition p is chosen is such that this mu of p is less than delta. So these are the two constraints which are imposed here on the partition p and the delta, such that 2k into p minus 1 into value of delta is what type? Value of delta is 2k into p minus 1 delta equal to 1 by 2 epsilon, and that delta, depend on that delta our norm of the partition p is dependent, and that norm is mu of p is less than delta. As p star is a refinement, we have p star is equal to p union p1. Okay, so you can see that this p star contain how many points more than this p star contain how many points more than p minus 1 points. Okay, now we know that we remember the results from the previous video. We have proved that result. This upper sum relation between refinement p star and any partition p, the upper sum up1f, this upf minus 2k p minus 1 delta is less than up star f, but up star f is refinement and it is less than up1 f. Again up1 f from equation 1 is less than upper integral plus 1 by 2 epsilon. Now let us put this value here. We have upf minus 1 by 2 epsilon is less than upper integral plus 1 by 2 epsilon. Transfer this term to this side, we get upf is less than upper integral plus epsilon, and hence the result is proved. This upper sum is less than upper integral plus epsilon, and this is for any partition p with norm mu of p less than delta. What is our delta? Delta is 2k p minus 1 into delta equal to 1 by 2 epsilon. Epsilon is any positive number. Okay, so in such a manner we can prove that this LPF is greater than lower integral lower integral minus epsilon. So this is about the Darboux theorem.